Okay, so I've got this optimization for first new neighbor. I was told on the internet that it was impossible to optimize new neighbor, but you can do it. And I thought the optimization wasn't that good because it had too many scattered reads. Like it abuses the cache of the GPU or CPU or whatever. You're supposed to run it on the GPU to make it go faster, but it actually doesn't, because it's half linear search, half binary tree. How it works, like what I do is and it's really simple how it works. You just gotta you narrow down the search by using by doing a clustering, but it's weird how you do it. What you do is you match less of the key, and then you leave the rest as possibilities. And so, you can see if a subset of the key, but it has to be, it's got to be a subset that encapsulates the rest of the data. So it depends on what data you put into it, but you can actually do it with any data. You can, because if you use sums, it's kind of like quantum how it does it. It uses magic sums to work, and if I can make sure the clustered version will match, guaranteed, no matter what one is after it. So it means that if you do it with contained matching, right, and then it gives you like big key sizes, and so the thing is, like, you don't need neural nets if you do that, because it replaces having to do back propagation by just having a list of keys and getting a similarity match instead. So it gets you out of neural net class, and it's really good for doing a stereo match, like matching a huge set of keys. But the big problem with it, why it doesn't solve all the AI, is because you can never have enough keys. When it depends on like how big the space, the data space is that the keys are going into. Because if the data space is too big, you need an exponential amount of keys. It only works for a linear amount of keys. Yeah, so that's why if you've got a big vector, you can only use 0.0000001% of the total population, and that's why without some form of semantical without some semantical grouping and proper selection of what the key actually is, and what the data is in the key, it doesn't solve AI by itself, but it does give you a shitload of matching power, and it does work really good, I would imagine. But if you want to get the robot fully done, it doesn't solve it by itself. You can sort of like learn a physics engine with it, but if the key's too big, it means it's got too much to learn. If you're learning one key a frame, and you're in an exponential set of a huge amount of, just say you were throwing a ball at a robot, you have to throw every single possible direction at it. It will never learn it. But there's a thing called geometric invariance, and that's what makes it trickier. You have to make it so it learns it all off one throw, or less throws. You have to learn off less keys, so that means you have to have smaller IO on the network, and there's less total permutation in the system, because you have to get rid of the perms you don't need. And that's the tricky thing, why it makes AI hard, that if you've got too many permutations, you can't learn them one perm at a time. Yeah. But it's really good. I'm glad I come up with it, but there's certain situations where it does work, and if you're learning computer vision, you'll see there's less permutations required to learn things. You can't learn things off just like RGB colors. Why? Because there's too many combinations of the colors. You have to. You probably want to go color to depth, then to postures. Since they're good, but you notice when you did that, you reducted permutations appropriately for it. Yeah, so you can't go straight from color to knowing everything, because there's too many different colors it can be. You know what I mean? You have to do semantical narrowing. That's geometric invariance and reducing the permutations, because you can't learn every picture on a neural network. You have to shape its learning for it. You have to spoon feed it a little bit, or it can't learn. I think you can go from picture to depth, but notice you can't go from the whole picture. but it works from like lots of little segments of the picture. So yeah, you broke up the problem for it. So that's why it has to be a convolutional net, because you reduce the amount, the picture size, and then you scroll it around. You know what I mean? That's like modularization. Like that's reduction perm, like I said. So if I'm learning like little corners of things, and then I'm connecting the corners together, that makes more sense because there's less key size, there's less total permutations. You reducted it. You have to shape the learning of a neural network. It doesn't work. That's why this thing handles keys that freaking bit long, but it's useless to. And that's why I'm sort of stuck a little bit there, but I already know. But even if you've got the super matcher, which does humongous keys and huge amounts of keys, you need an exponential amount of keys. That's what I mean. So it doesn't do it by itself. You have to shape the learning. You have to understand a little more. You have to put a bit more of your thinking into the robot's thinking, or it doesn't work. Yeah. But anyway, so we've got a super matcher. It's been congested against, but I've got my doubts about that. I think it's just bullshit. Yeah, so we've got a first end system. Get you out of perceptron class. This is really good. If I taught the kids this, it'd be really good. It's based upon, and it uses magic sums, and all my quantum stuff is magic sums too. And so you just got to make sure of the first linear search encapsulates all the later letter searches, and then you can go in like a tree. It's only IOPS when you go on using the nodes of the tree, but of all the chunks you're reading, you get them fully cached beautifully, so it's going to work. Anyway, that's the best I could do for a second video. I did a whole other video that was better than this one, but the audio stuffed up on it. That's the best I can do. Yeah, so we've got our first entry coming out, and it's really good.